Great credo, beyond the trash, granting biowaste a fresh start. Sounds very promising. Our next speaker will shed more light on this topic using lactic acid. What is his background? He holds a diploma on biotechnology and a PhD on bioengineering. Since 2003, he has been working at the Leibniz Institute for Agricultural Engineering and Bioeconomy and as senior scientist, industrial biotechnology. He's head of the research group Bioconversion, dealing with bioprocesses based on biogenic resources. Please join me in welcoming Dr. Engineer Joachim Venus from the ATB Leibniz Institute for Agricultural Engineering and Bioeconomy with a presentation on the topic production of lactic acid from biowaste. Welcome.
Thank you so much for the kind introduction, and of course I'd like to thank the organizers to inviting me to give a talk here, and it's really an honor and a pleasure at the same time to talk about things what we already heard partly in the presentations before. Probably you will remember when I'm going to touch some of the aspects again. I'm going to give you let's say, a mixture of some general aspects about renewable chemicals, the resources we could use for, and in the end I will give you an example of what we did in a European project. So, just to give you an idea for those maybe of the international audience where I'm coming from. So Potsdam is located directly in the neighborhood of Berlin, the capital of Germany. And we are belonging to the Leibniz Association, which is, let's say, the fourth pillar of the university research in Germany, besides the Max Planck, Fraunhofer, and Helmholtz. So just briefly, our program areas, what we are working on. And of course, I'm not talking about the crop production, the livestock, and the food today, but I'm touching the two ones bottom right, the biomaterials and the residues, since we are using residues, as you can imagine from the title of my talk, and to make materials out of it. So to be honest, I'm not a polymer guy, close to the title of the conference, but as you know, we need the previous steps of making the monomers ready in a good quantity and quality to make the polymers out of it. That's what we are doing in our institute and especially in my group. So we have heard in the first fantastic talk of Chris Paterman the beginning of all those activities in the beginning of the century. And if you have a look to this slide, you see that it came already in the beginning of the century from the DOE, the idea of changing or to have a transition from the fossil-based feedstocks to the final products on the right-hand side. And we like to call it biorefineries. And if I am, of course, talking about biotechnology and not the other conversion processes, I'm going to talk about fermentation, enzymatic processes, things like that. And as you can see also here from that list of the possible feedstocks, already 20 years ago, it was the idea to have a proportion of residues, waste, side streams, and so on as a possible feedstock for those processes. And then again, from the 20 years ago, a study, maybe some of you know that famous studies, I would say, 2004, there was a list of the most promising chemicals or molecules which were foreseen for the next years, and then more or less the same authors or part of them were doing sort of retreat of the list. And as you can see from the list of 2010, now we have organic acids like succinic acid and lactic acid in the list, and the second one, the lactic acid, is the product I'm talking about today mainly. So what is the idea behind comparing the different valorization paths of, for instance, bio-waste, which is a part of all the residues and remaining materials. So we are not going to put them in the compost or to burn it directly, which is in some cases still the practice. We like to go right now straight ahead to the right via putting that material in our facilities, in the fermenters, in the equipment, and to convert the sugars, what we already heard, into the monomers, in that particular case, the lactic acid, which could serve as a precursor for a lot of other materials, among them the PLA, what we already heard as well. If we try to compare the lactic acid case with some other so-called renewable chemicals, you can see here from that table that in the most cases bacteria, I try to remember that I'm talking about bioconversion processes, fermentation. Most of the bacteria loves the sugar streams, and among the sugar, mostly the glucose. Of course, we have some examples of having also oil or glycerol as a feedstock for bioprocesses, but the main proportion still are sugars. And if we have among our waste, what we are trying to use for those processes, we have lignocellulosic type, fiber-like, like peels or any other residues, we need to undergo some similar pretreatment what we heard right now. We have to separate the cellulose, semicellulose, and the lignin, but the difference to UPM in our case is that we convert the hemicellulose and the cellulose by biocatalytic processes by our microbes. The lignin needs to be sorted out since it's more or less stable against any microbial activities. But we can use the C5 and the C6 sugars out of the hemicellulose and the cellulose for our processes, and then we end up with a product which needs to be separated, purified, and so on and so forth. And just to give you an overview of that, what is necessary to come up with those processes, and I still highlighted the two steps which are, in my opinion, still the most challenging ones. The first one, still the pretreatment. Of course, we have heard about existing technologies, but believe me, if you change your feedstock and if you try to use new or other feedstocks, what you did not have in your hand before, you need to think about the technology, maybe about the combination of different process steps, about the parameters, and so on. This is very important. Then we need to destroy the biopolymers, the cellulose and the hemicellulose, by enzymes, then followed by the fermentation. And in the end, a very important step again is a challenge still, all that downstream processing, what we call, in order to provide really that quantity and quality of the product which is ready for the next step of subsequent polymerization, and that's not that easy. Here, just an idea that you could imagine what type of feedstock we already processed, what I was just mentioned with the differences among the feedstocks, the composition, the behavior, the properties, and all new feedstocks need new, at least adaptation or modification of your pretreatment and subsequent steps. And as you can see here from that list, in the meantime, the residues and the waste materials are the main proportion of our feedstocks due to all the political will on the European and the national level, what we heard about. Of course, by the way, we would be also happy to use simpler feedstocks if they are available, and if maybe there's a change in the mindset in order to really define the opportunities. But today I decided to talk about waste and residues. So just one example from a bilateral project together with Colombia, where we took the remaining materials from the coffee production, the so-called mucilage, and also the pulp of the coffee cherry. And then we did all the things what I was already talking before, the fermentation and a bit of scale up. The scale up in this particular case up to 50 liter, and then the downstream processing, the purification in the end to have the lactic acid ready, and the mentioned opportunity to polylactic. In this particular case, it was just a theoretical option since we didn't have a partner to do that. So our project was just to coming from the left, from the feedstocks from Colombia, to the right, to the lactic acid out of it. Another example is from a European BBI project named Percal, where we were dealing with a really dirty feedstock. Believe me, if we are talking about OFMSW, the organic fraction of municipal solid waste. So think about your black bin in front of your house, what could be inside. Of course, if we come up with a fermentation in the end, we cannot have everything. Think about metal, glass, stones, plastic, whatever. So we needed to sort it out manually in that particular case. But the remaining organic fraction we processed, and as you can see here, the yield of more than 0.9 gram per gram was really nice, and also the other performance parameters were really exciting, and we were not expecting that in the beginning, to be honest. Now I'm coming to another particular example, which was pasta waste. Pasta waste was fortunately not that difficult in view of the pre-treatment, since pasta waste is more or less starch mainly. And we got the option of different materials in this particular project, Cafipla, and pasta waste was one of them. And as you can see here, it doesn't sound so much to have just 23 gram out of 1 kilo pasta processing remaining waste. But, you know, if you think about the big industries and the millions of tons of pasta produced, then we have, of course, also a proportion of pasta waste. And we tried to use that for our processes. And I just try to give you some figures about the composition. As I already mentioned, it's mainly starch, much easier than the fiber-like or the lignocellulosic materials. So we can just use enzymes to hydrolyze the starch into the glucose. That has been done here. And as you can see here, it was a relatively quick process of about 5-6 hours just to hydrolyze the starch into the sugars. And then it's going to be a bit more in technical details for those of you who are not that familiar with the fermentation regimes. We can have the SHF means that we do separately the hydrolysis and then afterwards the fermentation, whereas the SSF means the simultaneous saccharification and fermentation. And just without going into the details of all that figures, you can see in this case as HF, that means separate hydrolysis and fermentation, was a bit more successful in terms of the final concentration of the lactic acid compared to the SSF. In other cases we already had in our project, it could be in the other way around. So, but the SSF, of course, is a promising concept to save time and money. So, and then when it comes to the question where to get the enzymes, which is sometimes a crucial part of the entire process in order to degrade the polymers from nature, we thought about our own solution to make our own enzymes. And what you can see on the left-hand side, very simple system in shake flasks to cultivate different fungi, and the results on the right-hand side, each diagram belongs to one of the different species, and as you can see, the left-hand side was much more successful than the right one, and the crude, let's say, fermentation broth of that so-called solid-state fermentation could be used in order to inoculate our pasta waste, in this case, to degrade the starch. So that means that could be a concept to reduce the costs, because in the other case, of course, we would need to buy the enzymes from the market, and in some cases it could be very expensive. So it was just a simple approach to see how could it work. And since we already saw different types of similar circles or cycles today, I'd just like to announce that we are working, among other projects, in that Rubio project, which is very close to the audience here. And in this particular case, all the things we were already talking about is more or less the same, or at least similar. The only one difference between that, what I was talking about so far, and here is that we are dealing with succinic acid instead of lactic acid, but we can run on, let's say, comparable fermentation system. We can use several feedstocks as also for the lactic acid fermentation. Of course, the microbes are different, the parameters are different, but in general, the system works in a very similar way. So this is what we are still doing here in this project. And here, just to give you an idea what we did, I was talking about the Percal project, which is already finished, the Cafipla with the pasta waste. The Beonat is dealing with woody material, to say in general, and the biomag, but I realized that I need to be careful with biomag since it has another meaning from UPM with the product. So therefore, I decided to call it biomag or biomag, so as you like. And this is a specific project where we put together a lot of different infrastructures from different European countries in order to have a collection of the entire, partly very, very long value chain from the feedstock, the pretreatment, hydrolysis, fermentation, and so on and so far, and ending up with nano particles containing biopolymers. So this is the concept of that project. And with that, I would like to end my talk. Thank, of course, all the supporters of our project activities, my team, and of course, you for your kind attention. Thank you very much.
Thank you very much, Dr. Joachim Venus, for the exciting presentation. And now we are looking forward to questions from the audience. Does anybody have a question?
If not,
no.
I mean, it's a very fascinating topic, at least to me. I mean, sources to come to lactic acid is really key to get more volumes in the market. And we all know that lactic acid was for quite a long time short in the market of compostable plastic. So my question is, how is the reaction of the large PLA producers on the market? Because the demand is increasing globally and lactic acid is short. So is there, I mean, I'm so surprised in a positive way, like, there's so many streams who could be used, what you've demonstrated. There should be a huge interest to scale it up, right?
Yeah, to be honest, we are not in contact with the global players like NatureWorks or Corbion. So, but we have a lot of bilateral contracts to smaller companies. I'm not allowed to talk about that. And in my opinion, they are more, the smaller ones are more often to, let's say, to open the wide range of opportunities from the feedstocks, whereas the big players still keep on their existing systems to having the corn in the US and the tapioca in Thailand, just to say it simple. But the smaller ones are really interested in having solutions for those feedstocks, which are, by the way, not that easy to process, just from the logistics, from the quantities, from the changes in different regions over the season and things like that, up to the question, what is not the economy of scale upwards, but downwards. If we are talking about feedstocks which are just available in, let's say, few quantities at a particular area, and I have contacts to companies, they think to build up those facilities in a container instead of, facilities like in the port of Rotterdam or what we heard from UPM. So to be honest, I'm not really convinced if it could be in a so small scale of just a few thousand tons a year or whatever could be the output of it. But this is what I got the feeling from the last years where people think about new concepts.
That's very good to hear. I mean, we need to use new ideas, new approaches, and I think also, even if it's smaller scale, it's very nice to have that.
Since
it's good to hear.
Do believe that also what we heard also from UPM, that there's remaining material out of the production process, so that means we need to do something with it. And I don't like the idea to have a production of, let's say, 200,000 tons a year and to have a remaining waste from that production in, again, I don't know, X thousand tons, which needs to be processed. And if we are talking about bio-waste, of course, we have in mind that we could bring back those residues from our processes, whether to the agriculture as a fertilizer or having a second cascade by, let's say, biogas or whatever.
I like those approaches. Thank you very much for that. It's really inspiring.
Yeah, thank you very much. Dr. Joachim Venus, thank you for your presentation. Great.